Um, but yes, constraints are a circuit, just with the caveat that it's not actually a circuit.
So I know that the pros of having the recursion is having it lightweight, but what are some constraints about using the recursion? Why are other zero knowledge projects are not necessarily using recursion?
Well, there's a few reasons, because some of them are just technical constraints. One of them is that it's actually pretty hard to design recursion. You have to think about it from the beginning, and you sort of want to integrate it tightly with your proof system, because embedding this verification operation into constraints can be prohibitively expensive. If you're not designing for it up front, trying to layer this concept that you can do the verification of a zero knowledge proof inside of a zero knowledge like circuit, so if we use that term, then you really are stuck with a situation where it's just not efficient at all. There's another thing when you compare it to folding, because the most expensive operation here is the sort of two operations you do when you generate when you do a proof. You have the witness generation. We call these inputs the witness to a proof, and then it's actually generating the proof itself. This part right here is the most expensive part of the computation. If you do folding, then what you're doing is you're actually sharing all the witness generation up front, and you have to do that n times, but you only have to generate proof one time for that aggregation. Whereas with recursion, you're going to have to keep on generating that proof over and over and over again. And I'll talk a little bit later about how you do more efficient recursion structures and how Mina tries to make it more efficient. But in the most naive way, if you're just doing like linear recursion, where it's just like one proof feeds into the next, this becomes really expensive. You're having to build O of n proofs in order to aggregate proofs together, right? So that's not very efficient.
Is it just cost or also speed?
Well,
both.
I mean, cost and speed generally are the same thing. There's two angles of cost. One is performance, and one is like RAM, I guess. Performance, basically you just throw more hardware at it to make it faster, and that's where cost comes from. RAM is just like how large your witness is. I would say that in the realm of recursive zero knowledge proofs, you're more talking about just the performance cost. The RAM cost is just how big your witness is, how complicated your constraints are, basically. And there are ways to get around that, which we can talk about later, maybe if we want to talk about chunking at the end. Okay, so now let's talk about blockchains. We're going to talk about, what a blockchain is and how you can actually apply zero knowledge proofs to a blockchain in order to get some really interesting properties. So essentially the way you can think about a blockchain is that a blockchain is just a state transition model, okay? So just some diagram I'm going to use for state transition models when talking about it. A state transition model or state transition machine is basically when you just have some concept of states, and then you have some concept of transitions, and you can apply a transition from one state to get to another. And the way a blockchain works is we think about these states as ledgers, okay? This is basically the state of everybody's accounts, what their balance are. And then the transitions are actually the blocks themselves, okay? And that's made up of many transactions, which are sort of like smaller transitions, which are all being aggregated together into blocks. And so if we draw this out, the way we can think about it is that a blockchain is starting from some genesis state, state 0, and then we apply a block to it. And then we get state 1, and we apply another block to it. We're getting state 2, and we just keep on doing this over and over and over again, where each of these blocks is like a big step transition that is made up of a whole bunch of smaller step transitions, right? These are transactions individually applied to substates of S0. We're getting another ledger, we're getting another ledger, we're getting another ledger. But this block is the grouping of them. It's the ordering of them that we're going to commit to doing them on the network. So naively, if we wanted to take this and we wanted to prove this, we have to think about these small step transitions here first. Let me draw these as like lowercase t's. So let's just take a look at one smaller state transition in a simple like payment-based blockchain. Let's say we have a ledger, and there's two accounts in the ledger. There's account A and account B. This ledger has some root, which we're basically storing as the state. And let's say that A wants to send, 5 currency to B, right? So basically what we're doing here is we're going to subtract 5 currency from A, and we're going to add 5 currency to B in order to satisfy this operation, okay? Well, we could actually do this as a zero knowledge proof, right? All we're doing in a zero knowledge proof is we're saying, oh, A is somewhere in the ledger and B is somewhere in the ledger. And then if we actually apply that transaction, then we have a new ledger with the same A and B, but we've actually, taken these values and then we've applied them to A and B, right? And that's basically the operation that we're proving. Okay, so this can be one zero knowledge proof. Does it make sense so far? So it's just a very simple state transition. And then what we're doing is we're taking all of these transactions and we're going to apply them all in a sequence. So if we have state S0, 0, and then we apply T1, T0 to it, now we have state S0, 1, and then we apply T1 to it, we have state S0, 2, and at the end, we're left with some final version of S0, which now we're going to call S1, okay? So in other words, what we're doing is, if we had 3 transactions in a block, we're going to generate 1 zero knowledge proof, 2 zero knowledge proofs, 3 zero knowledge proofs, and then that's basically our block. That's our state transition for our block, okay? And so if we draw this out, it's literally like transaction 0 is feeding in a proof along with the state that it created. I'll do this. Ends the proof for T1, which is then committing to the next one in the sequence, right? This is basically our recursion. This is linear recursion because what we're doing is we're feeding in the proof of the last transaction we applied to the next transaction we're applying to continue producing states. In addition to that, there is also one final proof that we have to do at the top, which is basically the block proof here, because blocks in a blockchain, which we'll talk about more later, are basically attesting to information related to consensus as well. Like, how long is this block in the blockchain? Like, we look at this whole chain, we want to know that this block right here is actually 2 in length and this one's 1 in length, right? And we have to keep on aggregating that kind of information as well as additional information that's going to prove that this block was valid. Mina is a proof of stake consensus layer. And what that means is that you actually use your stake to have the ability to win blocks. And so part of what this blockchain proof is going to say is that the person producing this block actually had the right to produce this block at this point in time. And so we're left with all these sub-transition proofs, which are aggregated back up into a block proof. And we just have this one proof for every block. That's the full state transition from S0 to S1. And then we just keep on doing that. All the block proofs are feeding into each other as well. Question, because I don't know if it was captured for the mic, is where are the zero knowledge proofs stored? We'll talk about that more when we actually talk about how the network is coordinating to prove all this information. The important information is that only proofs you're interested in general, is the most recent blockchain proof. So in terms of in terms of where they're stored, they're temporarily stored on the network. We don't actually even archive the proofs though, because they're not important. This proof right here already verifies this proof. In other words, we imagine that we're way in the future. We're talking about some block 1000. Block 1000 has verified block 1 and block 2 and block 3. So there's no reason to actually keep all those proofs around because we've already aggregated all the proofs together. So all the network does is store the most recent proofs the network is sort of coming to consensus on that are still being settled on the chain. And then as that's being aggregated up into the block proofs, we just throw them all out. Any other questions? Okay. So before I move on, I'm going to move on and talk about how this actually works in the Mina chain, because this is not how it works in the Mina chain. This is a very naive form of linear recursion. Every single time we do one transaction proof, we have to wait for the last transaction proof to come in, right? And so in that world, that really limits our throughput, because the number of transactions we have in blocks is, in other words, we have to do all n of those to produce the block, right? That's not very fast. It's sequential, and we can never really scale the blockchain because of that. And so in Mina, instead, we do something fancier to basically parallelize over all of these transaction proofs and do the transaction proofs in parallel to the blockchain proving. So we're going to actually separate these two layers out. Ready? So if we separate this into two concepts, really what the chain's doing is the chain is proving two things at once. Okay? Up here at the block layer, we're proving consensus information. And we'll talk more about how consensus works later. But then there's this separate layer down here where we're proving the state transition model, which is basically our transaction layer. Okay? And so if we separate these two, we can start to think about the state transition model, which is the heavier part to prove, concurrently to the consensus model. The consensus model is always going to have linear recursion. You always need the previous block before you can produce the next one. You always need the previous block proof before you can include the next one. So this is locked into linear recursion, okay? But in the state transition model, even though all the transactions themselves are linear, we don't have to build the proofs in a linear sequence. We can actually build them in parallel. So to understand this, you can think about the transactions. We can think about it like this. Let's say that one block just has 4 transactions in it. We can go through and we can generate the witnesses, basically the inputs to each of these transactions, before we generate any of the proofs. This is a very quick operation. This is what's happening on Bitcoin all the time. We're just applying the transactions and we're seeing what happens just on a computer. And so we can understand that for transaction 0, if we just go through and apply all these, we can figure out what all these states are before we generate any of the proofs. We know that we need these 2 states for transaction 0. We need these 2 states for transaction 1, these 2 for transaction 2, and these 2 for transaction 3. So once the network has done this, if any nodes of the network have gone through and applied these transactions manually, they know what the witnesses are to generate these. And now each node separately can generate proofs of these transactions. But now we still have 4 proofs, and we just want 1 proof at the end because we're trying to include 1 proof back up into this block. So our goal is to get that 1 proof that we can include into the block because, well, let me point to this one for a second because maybe it'll make more sense. Because essentially, the blockchain proof is taking in 2 recursive zero-knowledge proofs. It's taking in the prior blockchain's proof, and it's also taking in the proof of the transactions that are within this block, okay? And so what the network can do is the network can actually do binary recursion on each of these to merge them into each other. And so in a sense, if this one here is a proof of S0 to S1, and this proof here is a proof of S1 to S2, this one here is now a proof of S0 to S2 because we combined the 2 together. We checked that S1 was the same, that basically the target of this proof matched the source of this proof, and then we just merged them together recursively. And the same thing over here. We know that this one is a proof of S2 to S4. And then finally at the top, we're left with a proof of S0 to S4. And so when we include that in our block, we can now do our big step transition as a single recursive zero-knowledge proof that's included in the block. So I'll talk more about how we do this in true parallel later, but you can already see at each layer, we have 4 parallel pieces of work that are available here, 2 that are available here, and then finally 1 that's available here. And we do a trick to basically parallelize this so it's not just always, changing over time how much parallel work you have available in the network. The trick here is that you still, in this model, have to do all of this work before this block is produced. And so that doesn't actually really work very well. Instead, what we have to do is a block, let's say it's this one now for a second, just as an example. A block is going to commit to what these transactions are, and then these will be included in a future block. In other words, there's some kind of delay gap on the network that's happening between when the transactions are sequenced and when they're actually proven inside of a block. Have you ever heard of like the stage ledger and the Stark ledger? This is the difference between those ledgers. The stage ledger is the ledger in which transactions have been enqueued but not proven. The Stark ledger is the ledger in which transactions have been proven. Okay? I'm going to talk more about this in detail in the next panel, but any questions about this before we move on?
Maybe it'll come up later, but are there any issues to do with, say, collisions or ordering in this model?
No, because essentially what consensus is consensus is a way that the network achieves a shared understanding around what the ordering is. So we'll talk a little more about it later, but let's say, there's like multiple blocks which may have different orderings from each other, but in the end, only one blockchain is going to live on. And so each of these blockchains can project a different ordering sequence, but within whatever chain you're currently working on and you believe is the strongest chain that you're operating on top of and the network is continuing to operate on top of, there is one defined sequence. Because some prior block has defined the exact sequence, we know the exact sequence that's going to be proven down here, and that's just agreed to for every future block that's built on top of it. Does that make sense? But that is basically what consensus is for. Consensus is the solution to the ordering problem. If everybody orders things differently, then it's not going to work. And so you have to achieve consensus on the various orderings that people agree to.
This is a stupid question, but the reason why in each transaction, we require zero-knowledge proof is because of the off-chain computation, and we don't have a virtual machine that does it on top of our blockchain.
No. Right now, we're not at the point where we have programmability in the blockchain. We're talking about just payments. So all of this is happening on-chain. There's no off-chain computation right now. We're only talking about on-chain computation, things that are happening on nodes on the network. But it's not virtual machine computation. Like Ethereum has a virtual machine that runs smart contracts, but they also just have regular machine code that they've deployed that's running the transaction logic for payments and things like that, right? So right now we're talking about sort of the baked in part of the program that people are running on the network. We're not at the point where we're running virtual machines that run arbitrary user code. Does that make sense?
Yep.
Okay. So let's talk a little bit more about that tree that I drew before, right? I mentioned there's like 4 layers at the bottom, there's 2 layers, and then 1 layer. The problem with that is that if you just use that as the structure that you're basically doing things on the network in, you end up with a network where the saturation of work is constantly oscillating like a sine wave, right? In other words, when we first enqueue the transactions, we're up here at the maximum level of parallelism. But as we keep on going down the layers of the tree, we eventually get here where there's only one proof to do, okay? This really isn't what we want. This is not how we actually want to build a network, because what's going to happen is people are going to spin up machines here and there's going to be some delay. People are going to spin them down. It's not profitable anymore because there's not enough work to do in parallel. The whole point is that we want a whole bunch of servers on the network to be doing these things individually in parallel. And so what we want something that's going to look a little bit more flat. In reality, it's not quite flat. Maybe it's moving up for demand and moving down as demand comes, but it's sort of staying around this line based purely on demand. We don't want it to be oscillating up and down regardless of demand, okay? And so there's this neat trick you can do where you're still working on these trees, but instead of having one tree at a time, you basically have multiple trees. Oh, I drew that tree too big. And so let's still imagine that each of these trees is like, 3 layers deep for now, 4, 2, and 1. If you have all these trees at once instead of just one tree, you can actually control the sequencing logic for these trees and the work that needs to be done in the network such that each tree, you're working on a different layer of the tree, okay? So let's say this tree over here, we're working on the bottom layer. So here we have 4 pieces of work. And then here we're working on the middle layer, so there's 2 pieces of work. And here we're just working on the top layer, so there's 1. Well, in a sense, if you think about this picture, you can just combine all these trees together and you have 1 tree. You have 1 tree all the time. But by having multiple trees in different parts of the computation, you're keeping a constant amount of work that can be saturated on the network at any point in time, and you get something that's more like this. As there's more transactions, there is some increased work because there's more throughput, but the amount of possible work that can be done by anybody on the network is the same at any point in time, right? And so, in a sense, each of these trees is coming from different blocks in the blockchain. So this is not quite true. There's actually some tricks that it's not always true. But let's say each of these trees contains all the transactions for a single block. It's like this block inserted into this tree, this block inserted this tree, this block inserted this tree. The state that you're seeing here of each of these trees being proven is actually from this block's viewpoint, right? Because we've already finished this layer when we did this block. And then we finished this layer when we did this block, right? And so essentially what you really get at the end, the way you can ultimately think about it, is that there's just a queue of work. There's a queue of transactions coming in, and there's a queue of work. There's a definite ordering on the order that work has to be completed in by the network. Block producers have to include that work before they get more space for more transactions. I can't allocate a new tree here until I finish this tree. So I have to finish this tree to make more space. And I also can't include any work from this layer of this tree until this layer and this layer are done, right? So there becomes like a definite ordering on all the transactions, the order they need to be applied in, but not just that, also the order that all the work has to be done in by the network. There becomes this marketplace between block producers and snark workers, where block producers are living up here in the consensus layer, and snark workers are proving the state transition model. They're all working in parallel on the network, where snark workers can sell the proofs back to block producers, and block producers pay the snark workers from the transaction fees they're including. So they're including transaction fees, they're getting coin bases, and they're distributing rewards back to the snark workers for their efforts of selling proofs back to the block producer. The block producer needs that work. It cannot continue including transactions if it doesn't buy that work. In fact, if you purchase no work and the queue is full, you can't even make a coin base. So you may have seen issues on the network where sometimes you can't get a coin base. Ultimately, these are usually issues with either the snark work not being available on the network because people have had an issue, or with some network issues related to the networking stack right now that we're fixing. And so this definite queue of work becomes this tool that the network is using to coordinate all the parallel work that's going on for snark proving. In a sense, the state transition model of Mina is not just a state transition model between the ledgers. It's actually a state transition model between this very complicated queue data structure too. Every block is not just saying, hey, this is the ledger I started with, and this is the ledger I ended with. The block is actually saying, this is the ledger I started with, and this is the work queue I started with, and this is the ledger I ended with, and this is the remaining work queue that I ended with. Does that make sense? That's sort of what the state transition of Mina is. In addition to that, we're actually tracking two ledgers in Mina. I mentioned this before already, but if we're thinking about, this is all sort of from this block's viewpoint right now, what this looks like. We have two ledgers, which is the snark ledger, is the ledger right here. It's the ledger that we started applying transactions to. But all these transactions are still being proven. They're not proven yet. And so the ledger that we get at the very end of applying all these transactions, this is the stage ledger. And this is the delay I was talking about. This is basically the asynchronous delay, is that there's a snark ledger that's being updated every time that one of these trees is finished. And every time transactions are included, the stage ledger is being updated, and there's a short, finite distance gap between these two things at any point in time.
Two questions. So first of all, how to ensure the balance between block producer and snark workers? Obviously, block producers get the coin base, but it would not make sense for snark worker to turn into block producers, or the other way around. How does Mina ensures that balance?
Well, that's the financial incentives of snark workers. So is a case right now which we're working on fixing. I can go into it later. Maybe it has to do with taxes and some misunderstandings, but where some snark workers are selling snark work for zero on the network. And so in that case, their incentive is sort of, they're also running block producers. They need the work, which is not how the network's intended to work. The way they're doing that primarily is for tax purposes, because they get paid out for snark work every single block, and they decided it costs too much money to do the tax work, so they just charge zero. It's very interesting. There's also another reason, which is that some people misunderstand that model, where they think that if they charge money, then they'll lose money, which is a weird misunderstanding that some people have in the community. They're like, oh, I need the snark work on my block producer. I want my block producer to buy it, so I'm going to sell it at zero to my block producer. But the truth is, you should just attach money to it, because if you buy it from yourself, you paid yourself the money you bought it for. Like, it didn't go anywhere, right? Whereas if you attach a fee to it and somebody else is the one who includes in the block, then you make money. So these two different reasons, like taxes and misunderstanding, lead people to put snark work at zero. I'm curious to see what's going to happen with Berkeley now that snark work is more expensive. It's going to cost more for them, and there's going to be more of an incentive to actually put a price back on there again. But when there was only payments, snark work was so cheap to do that people just, it wasn't worth their taxes, basically, right? It was not an expensive thing to run a Snark worker and actually produce the work for the network. There wasn't enough money to be made there. But the actual reason is basically the financial incentive marketplace. It is the idea that block producers need this. They're willing to pay for it. That's true regardless. The only reason Snark workers aren't doing it is because they're unwilling to charge for it, which is a different issue, right? As long as they're producing work, though, that's great. And if all the Snark workers that were producing zero-fee works disappeared overnight, people who are not producing zero-fee works would actually come back online and make a profitable model of it. You can basically charge whatever you want to as long as the block producer is able to pay for it. The block producer has a very big coin base. They have a lot of money that they can actually spend to pay for that work. And what's happening right now is that, the competition is just push it down so much. The way the networks work is pushed down so much. But imagine all those zero-fee Snark works disappeared. It doesn't mean people would stop producing Snark work. It just means that people would actually be able to charge for it again.
How hard is it technically to set up and become a Snark worker? Is it can all the validators basically run similar program and participate as a Snark worker?
So the architecture, the way it works is you basically run a Snark coordinator, which is a regular Mina node. So that's the same as running a block producer or a seed node or any kind of regular Mina node. And then the only extra work on top of that is that you run a bunch of Snark workers that are attached to that coordinator doing the work in parallel for that coordinator. So setting it up infrastructure-wise is actually not that difficult. It's basically two programs you're running. You're running one instance of one program and then n instances of another program. With modern cloud providers, it's pretty easy to do, honestly. I think it would be more annoying if you were running physical hardware servers, but that's not generally what people are doing. Even then, there's not a lot of technical requirements to it. The main difficult requirements are all on the node that you run, which you already have to do to participate in the network. So it's not really much extra work to run Snark workers underneath that node and have that node be a coordinator. It's worth mentioning you can have any node be a coordinator. Our node roles are not distinct. You can run a block producer that's also a coordinator at the same time, and people do that a lot.
What about the transaction kind of full confirmation? You mentioned here that potentially there might be some case that, the first block that's valid, the latest block that's being verified that has transaction, but, there is in the Bitcoin, you need at least, to have the full confirmation, you need a few blocks. How does it work with Mina? And we need to get the, 99.9%.
So, okay, there's two numbers. Well, there's a few numbers. Here's the issue with that is that there's, we use Ouroboros, which I'll talk more about later. Ouroboros is a probabilistic probabilistic consensus mechanism. So it's similar to Nakamoto consensus, but because it's not proof of work based, because it's proof of stake based, and it's not a BFT validator cycle, you actually have a very long number of confirmations for the 99.99999% finality. So if you really want to wait for the absolute finality, what we refer to as absolute finality, it's pretty long. It's 290 blocks. But the truth is that you don't need to wait that long because you can get 99.9% finality in about 15. So there becomes sort of this gradient trade-off where if you really want to have absolute finality, like the way the protocol works, the way that things that deeply integrate with the protocol work is they're looking at this longer finality pool of 290 right now. But most applications operating on it, like exchanges and applications that actually have financial incentives to not have reorgs happen that are going to screw up things they've already done, they only look back 15. That's usually what people look back. That gives you the same probability as Bitcoin. Bitcoin's probability is less than Ouroboros's. But Ouroboros, for reasons, has to have a higher probability. It's very technical and related to consensus. And if you're building an application on it, you basically never worry about it. It's like, you've got 100 years before you're going to hit that edge case, you know what I mean? But Ouroboros is designed to work in, 10,000 million years, whatever. It's just, it will never hit that edge case. So that's why we use 290. So I know it's a little complicated answer. Hopefully that answers the question. Yeah.
Actually, two questions. The first about legal issue. Validators were saying that the Snark process is actually considered as proof of work mining because of the verified randomness. But whereas the randomness actually plays a role in the Snark process, and then why it is considered mining?
There's no verified randomness in there. Only in the block production.
Yeah, I don't know. That's what I don't understand. Why it is called as mining in the legal terms, the Snark process, because that's why taxes are so high.
I'd never heard this before. I think that's a misunderstanding of how the protocol works. It's definitely not mining.